Hello and welcome to yet another video on statistics for Year 12 Maths. So this is going to be Chapter 3 we're talking about in this session, representations of data. So what that means for this chapter is primarily we're going to be looking at, as you could probably guess, how we can differently represent data. So the main things are cumulative frequency diagrams, box plots and histograms. And among this we're going to also have a look at how we can compare and contrast different distributions, and also take a look into what we mean by outliers and anomalies. This session is going to be based on looking at outliers and anomalies, as well as some box plots. So without further ado, let's get started with some warm-up questions. So here they are. So write them down, try them on your own, press pause now, and then just press play when you're ready to see if your solutions match to mine. Okay, so let's have a look now and talk through the answer to question 1. So you might be thinking these warm-up questions are fairly light, not too tasking, and that's the idea. This is just a warm-up into statistics yet again. Question 1, calculate the upper and lower quartiles for the following set of data, A. So what I'm going to do here is I'm just going to show you how you could do it manually, and then of course I just want to get you used to using the ClassWiz. So using the ClassWiz, what we need to do is, sorry, I'll show you the ClassWiz after, I mean to say. So doing it manually, although it says upper and lower quartiles, what I'd suggest we could do is first of all find the median. So the median is the middle one, so the median is going to be this 7 here. Then on either side of the median, we take the middle of the values on the left. The middle on the left is going to be the lower quartile, Q1, so in our case, because 5 is the middle of 3, 5 and 6, so Q1 is going to be 5, and the middle number on the right hand side is 9, so Q3 is going to be 9. So for that reason we've worked out that the upper quartile is 9, and we've also worked out that the lower quartile is 5. Now I did say I'd show you how to do this using the ClassWiz, so let's have a look at how we could do that using the calculator. So what we need to do is get the calculator up and ready. Here it is. I'll just get it centered for us. Okay. Then what we need to do is remember how to get into statistics mode. So we press menu, scroll down to option 6, go to one variable, and then we type in our numbers here. So you might notice here we've got a frequency column. This can be turned on and off. So to turn it off, for example, we press Shift menu, scroll down to statistics, which we've got here, so press 3 for statistics, and turn it off by pressing option 2. So now here we can just type in our numbers. So the first number is 3, 5, 6, 7, 7 again, 9 and 16. Once we've typed in all the data values, press AC, option 2. And I'll make this screen slightly bigger for you. So as you can see here, nothing to do with quartiles on this screen. Press down to toggle to the next screen. Q1 is 5, which we've got, and Q3 is 9. So that's how you do it using the ClassWiz. So that's question 1 done and dusted. Let's now have a look at warm-up question 2. Okay, exactly the same idea. So if you can do question 1, you can do question 2. So I'm just going to rush through this. Well, not rush, but just do this quite quickly. It's exactly the same as question 1, to be honest. So we find the middle one of these. So 1, 2, 3, 4, 5, 6, 7, 8. The middle would be halfway in between 10 and 11. So Q2 is 10.5. Just going to show you again how to do it manually. So on the left, we've got 4 values, and on the right of the median, we've got another 4 values. And so the middle of these 4 on the left is going to be halfway in between 9 and 10. So Q1, the lower quartile here, would be 9.5, and the middle of the values on the right, Q3, what number's halfway between 12 and 12? Well, that's just going to be 12 again. So the upper quartile is 12, and the lower quartile is 9.5. Quickly showing you again how to do this on a class whiz. So we press Menu, Option 6, one variable, and type in our numbers. So 1 equals 9 equals, pressing equals after every number, 10, 10, 11, 12, another 12, and then finally 13. Press AC to clear it from the display, then option number 2, press down. As you can see, Q1 9.5, Q3 is 12. So that's question 2 of the warm-up done now. Question 3, calculate the interquartile range for dataset A and dataset B. So now just let's remind ourselves of what dataset A was and what dataset B was. So here's what we had from before. So we need to work out the interquartile range for both of these. So for dataset A, we can use the answers to question 1 and question 2 here to help us. So for dataset A, that was our Q1, that was our median, and Q3, the upper quartile, was 9. So the interquartile range for A is just Q3 minus Q1. So that's going to be 9 minus 5, and that's 4. For dataset B, we worked this out on question 2. So for dataset B, we had that Q2 was 10.5. We had that the lower quartile, Q1, was 9.5, and we had that the upper quartile, Q3, was 12. So for dataset B, the interquartile range for that one is again Q3 minus Q1. So in our case, that's 12 minus 9.5, and that's going to be 2.5. And again, you could check this on a calculator if you wanted, or just using what we had from before. You can see here, before dataset B, Q3 was 12, Q1 was 9.5. 12 take 9.5 is 2.5. Finally, question 4 of the warm-up. Calculate the mean and standard deviation for dataset A. Give your answers to 3 significant figures if needed. So just reminding you again of what dataset A was. Here it is. Again, we can use the class whiz for this. So get the class whiz up. Again, you should know this almost off by heart now. What we're going to do is we're going to press Menu, Option 6, press 1 for one variable, and again type in the numbers. 3, 5, 6, 7, 7 again, 9, and 16. AC to clear it from the display, then Option 2. Now, if I just press down again, you can see this data is what we had from before. Q1 was 5, median was 7, upper quartile is 9, but the first display is what we've got and what we need. So the mean is given by this X bar symbol. So X bar to 3 sig figs is 7.57. So the mean is 7.57, correct to 3 significant figures. So we can write that down first of all. Mean is 7.57. I'll just make a note that's to 3 sig figs. That's the mean of A, so I'll put subscript A, just to make sure we're not talking about B. And standard deviation of A, again, is on the same display. So we're looking for this weird-looking 6 symbol. This is called sigma. So sigma x, standard deviation, that is 3.85, correct to 3 significant figures. So that concludes the warm-up. We can now get into the main body of the lesson and have a look at statistical distributions and how we can represent these. So let's move forward. So let's have a talk about outliers and anomalies and what they mean. So what is an outlier and what is an anomaly? So an outlier is an extreme value that lies outside of the overall pattern of the data. So an outlier is something which is, forgive my English, a bit freakish, like completely either outside what you consider to be average or expected. So sometimes outliers are legitimate values. So if in doubt, or you're not sure, you have to assume that outliers are real values. Okay, so what you need to do though, if you're not sure, is to check if they're an error. So sometimes outliers are legitimate. However, there are occasions where an outlier is clearly an error. If it's an error and it shouldn't have been there at all, it should be removed from the data. So if it's an error, these data values are called anomalies. So in plain English, an outlier is an extreme value which is legit, and an anomaly is an extreme value or just simply a value which is wrong and a mistake. So because it's a mistake, an anomaly should always be removed. And the process of removing anomalies from a set of data is known as cleaning the data. So I'll just give you a quick sort of example, just a worded example of what might be an outlier and what would be an anomaly. So for example, if you've got a few people in a room, let's say actually more than a few, let's say 100 people in a room, an outlier could be somebody that measures 6'7". Okay, people do exist that are 6'7". An anomaly would be someone that's measured to be 12 foot. Okay, it is in fact impossible to be 12 foot tall. So an anomaly would be someone that measures 12 foot, that's impossible. Whereas an outlier could be someone that actually exists that is actually 6'7". So let's have a look at this in a bit more depth in a second. So how to define an outlier? So common definitions of an outlier are, first of all, either greater than the upper quartile plus some constant here multiplied by the interquartile range. Q3 minus Q1 is the interquartile range. Or it could be this same distance, this value multiplied by the interquartile range, below the lower quartile for some value of this constant k. Almost always this value of k is given as 1.5. So it can be defined based on the quartiles, or the second definition is it's defined upon the standard deviation and the mean. So if it's either more than 2 standard deviations from the mean or less than 2 standard deviations from the mean, that's another way of defining what an outlier would be. Here's an example of an outlier now. This is some real data. So this is based on cricket. If you don't like cricket or don't follow it, don't worry, the maths will still make sense. So the table below shows the top 10 test match batting average in international cricket. So to qualify for this list, players must have played at least 100 test matches for their country to be on it. So that's, for example, just making sure you can't get on the list by just playing one match and being lucky and scoring 100. So this is weeding out the ones that may have just had like a couple of good innings. If you're on this list, then your average is legitimately good because it's averaged out over many, many matches. So you've noticed here, I've got number 1 blanked out. So what could be number 1? Who's on pole position? Well, if you know anything about cricket, chances are you'll know this already. The number 1 average of all time belongs to Donald Bradman. He was Australian. He had an average of almost 100. In fact, his last test match innings, he was out for a duck, he got out for 0. If that didn't happen, he would have retired with more than 100. So for that reason, he is very much an outlier. So here's what he looked like. That's him in his test match days. But I don't want you to just take my word for it that that average is an outlier. We can use the definition, what we've just seen before, to show that this average would indeed be an outlier. So what was the definition from before? It was this one. This is the main definition based on the quartiles. So a value is an outlier if it's either greater than the upper quartile plus, we're going to go for 1.5 multiplied by the interquartile range, or less than the lower quartile minus 1.5 multiplied by the interquartile range. So for Sir Bradman, we're going to be looking at this one because obviously 99.94 is on the higher side of what the average is going to be, what the upper quartile will be. It's going to be greater than this. So let's just use the calculator and see if we can compute the quartiles and then work out, therefore, what would qualify as an outlier. So get the calculator up and running. So what we need to do here is, once again, we type menu, option 6, one variable, and just type in the values here. So the first value, Donald Bradman's, 99.94. Press equals, and 63.76 for the other one. This player here is currently playing, hence the asterisk. He's Australian and has got an incredibly decent average so far. 63.76. Then Sutcliffe of England, 60.73. Barrington, 58.67. Weeks, 58.62. Next one down, Hammond, 58.46. And 57.78. 57.41. 56.95. And finally, Walcott of the West Indies had an average of 56.69. So before we actually compute this, if you just have a look here, averaged out, these values are much of a muchness. They're all high 50s, low 60s, aren't they? And then you should hopefully see that this Bradman character stands out like a sore thumb. It's not even 70s or 80s, it's almost 100. So you've got a massive grouping here. These are fairly close to each other. Then way out is Donald Bradman. So that is what an outlier often looks like. It's just lying way outside the norm. That should get your intuition going and thinking maybe this one's an outlier. So let's go back to the calculator and compute the quartiles. So once we've typed in the values, remember we press AC, then OPTN, and option 2. So I'll now make this screen bigger so you can see it clearly if you're watching on your phone or laptop at home. So press down, and Q1 is 57.41, so we'll write that down. So Q1 is 57.41. And Q3 if we go back here, Q3 is 60.73. So we can use this to work out the interquartile range. So the interquartile range is going to be Q3 minus Q1. So if we go back to normal mode by pressing menu option 1, I'll just move it over here slightly. So 60.73 minus 57.41. That's a very small interquartile range, so 3.32. So based on this definition, an outlier would be anything which is Q3, 60.73, plus 1.5 multiplied by this interquartile range. So if we work this out, so that's 3.32, multiply it by 1.5, and add on 60.73. So an outlier would have been anything greater than 65.71. So Bradman's average, you can see, is 99.94. So 99.94 is just a little bit above 65.71, I'm sure you'll agree. Therefore, Bradman is definitely an outlier. No mistake. And because he's such an outlier, because this is such an achievement over so many tests, it's often called by some experts as the greatest achievement in sporting history, to maintain that average over multiple tests. That will never, in my opinion, ever happen again. So let's now have a look at some more examples. Here's another example of an anomaly. So this isn't an outlier. An outlier is something that is genuine. For example, Mr. Bradman, he did exist, and his average was completely extreme. An anomaly is essentially a mistake. So this here is 10 people selected at random from the electoral register in England. So these are the ages. So if one person's 54, 12. At a quick glance, this looks to be fair enough. Okay, these are all seem to be ages. However, if you look at this one, 154. No one is going to live to be 154. Not yet, anyway. Maybe in many years' time we'll develop some drugs, but 154, no chance. So based on this, we can do a bit of analysis. So currently in England, you can register to vote if you're 17 years old. However, you can only vote when you become 18. So that means that 12 is a mistake. You can't be registered to vote at 12, and so this one is a mistake. It's an anomaly. And as well, 154 is a mistake because no one's going to be 154 years old in this day and age. So these two here are mistakes. In fancy language, they are anomalies, and so they should be removed from this dataset before carrying out any proper analysis. And the process of removing anomalies is called cleaning the data. You're cleaning the data of any mistakes. So just to reiterate, a simple summary in plain English is an outlier is an extreme but genuine value that should be included, whereas an anomaly is an error or mistake that should be removed. That's the simplest way I can put it to you.
Let's now have a look at a couple of examples dealing with how to identify and calculate anomalies. So, identifying outliers, first example. So we've got the blood glucose levels of 20 females, which has been recorded here, these 20 values. The results in millimoles per litre are shown here. So an outlier, using this definition, is a value that falls either 1.5 multiplied by the interquartile range above the upper quartile, or 1.5 multiplied by the interquartile range below the lower quartile. So our task here is to show that 1.3 and 4.7 are outliers. So what we need to do here is to find the interquartile range for this data. Once we've done that, then work out what 1.5 multiplied by the interquartile range is. So we need the class whiz here. I would not suggest to do this manually. So get the class whiz up and ready. And what we need to do here is to type in these data points one by one. So we go to menu, press option 6, and then 1 for one variable calculation. Now, you can either have it with or without this frequency column here. It's entirely up to you. It will work fine with or without it. I'm going to leave it on here, just so I can show you a little thing with some discrete data that has values that repeat. So the first value I've got is 1.3, so we type in 1.3 then equals, then 3.1, then 3.2. Now you notice we've got 3.5 twice, so I'm going to type 3.5, and then I'm going to go to the frequency and press 2, because there's 2 lots of 3.5. Next we have 3.6, I'll just switch sides for a moment. So 3.6, we have 3 lots of that. So 3.6, press equals, and then I'm going to type in 3. Next we've got 1 lot 3.7, so just type that once. 3.8, 1, 2, 3, we've got 4 of those, so type 3.8, then toggle to the right, and type in 4. We then got 3.9 just once, 4.0, we've got 3 instances of that, so type in 4.0, toggle up and type 3, and 4.1, 4.5, and 4.7. If there's just one instance of a value, you don't need to type frequency 1, it does it for you. Now I've got all the values, we press AC to clear the display, then we press OPTN and 2 for calculations on this one variable. To get the quartiles, we press down, and you can see that we've got them here now. So Q1 is 3.55, and Q3, the upper quartile, is 4. So that's what we're going to type in here. So for this one, Q1 is 3.55. And Q3 is 4. So therefore, the interquartile range is 4 minus 3.55. It's always the upper quartile minus the lower one. So the interquartile range is 0.45. Now we've worked out the interquartile range, we need to multiply this by 1.5. So 1.5 multiplied by the interquartile range is going to be 0.45 multiplied by 1.5. So if you go back to normal mode, menu option 1, 1.5 multiplied by 0.45 gives us 0.675. Okay, so now we've worked out this value here. We need to do this value above the upper quartile and this value below the upper quartile. So now the upper quartile we have is 4. So what's 4 plus 0.675? Well, 4 plus 0.675 equals 4.675. So that's one boundary. Anything beyond this, anything higher than this, is an outlier. So looking here, are any values above 4.675? Well, we can see here that 4.7 is higher than 4.675, and for that reason 4.7 is an outlier. So just say that 4.7 is greater than 4.675, and so 4.7 is an outlier. And we do the same idea with this 0.675 value. We subtract that from the lower quartile. The lower quartile we had was 3.55. So now we do 3.55 minus 0.675. And again, we see what that gives us. So 3.5 minus 6.75. 3.55, I mean, minus 0.675. That gives us 2.875. So we can see here there's only one value lower than 2.875, which is 1.3. Because 1.3 is lower than this, 1.3 is therefore an outlier. So we say that 1.3 is less than 2.875. And so we've shown that 1.3 is also an outlier. Let's have a look at a second worked example. So for this worked example, we've got the mass of 20 Arctic terns, which are recorded using summary data in grams. So we're told the total mass, which is 2017, and the sum of the squares of the masses, which is 205,127. Calculate the mean and standard deviation of m. So what we need to do now is to either remember the formulae for calculating the standard deviation will refer to the formula sheet which you would be given in the exam. So the formulas I'm talking about are these.
And here are the formulae. So here we've got x squared and x, which is just our m squared and m. So just because a variable in the formulae is given as an x, we're going to just take our x to be m. X is just the generic letter for a variable. So in our case, our letter is m for mass. So all we need to do here is use this bottom formula. This one's for standard deviation, top's for variance, and plug in these values. And so the sum of m is 2017, and so that's, in this case, the sum of x. The sum of m squared is this big figure here, which is essentially this sum of x squared. Now, when it says here n is the same as sigma f, and just means the grand total of all data values, the total number of data values, I mean, and that's 20. And so for part A, all we need to do is type these figures into the class whiz. So the mean mass is just going to be this here. It's going to be the total of the values, which is 2017, divided by the total frequency, which is 20. So 2017 divided by 20. Try this on the class whiz. We get 100.85. So to three significant figures, you could give it to one decimal place if you wanted, I suppose. That's 101 grams. Now to calculate the standard deviation of m, I'm not going to use this rounded figure of the mean. I'm going to input the values exactly to avoid any rounding error. So what we're going to type in is the sum of m squared, which is 205,127. So it's that divided by the total number of values, which is 20. And we're going to minus from that the sum of the values, so sigma x, which is our sigma m, which is 2017. We're going to divide that by the total frequency, which is 20, because we've got 20 of these turns, and that's squared. All of this square rooted, of course. So if we calculate this now, so we're going to do 205,127 over 20 minus, in brackets, 2017 over 20 squared. And that gives us two three significant figures, 9.25 grams. So those are the answers to part A of this question. Let's now have a look at part B. So part B, it's saying an outlier is an observation that is plus or minus 2 standard deviations from the mean. So what we can do here is use what we've calculated and work out what the mean plus or minus 2 standard deviations actually would be. So using what we had from before, we can work out easy enough the mean plus or minus 2 standard deviations. The mean, in its exact form, we got was 100.85. So I'm not using the rounded mean, I'm using the exact figure to make sure I don't incur or have any rounding error in my calculation. So it's going to be that plus or minus 2 lots of the standard deviation. So the standard deviation given to a bit more accuracy was 9.2535. And so we can now calculate this. So 100.85 at the lower end, not 52, minus 2 lots of 9.2535. That comes out at about 82.3 grams. Okay, so 82.3, just over 82.3. At the other end of the scale, the mean plus 2 lots of a standard deviation gives us 119.4-ish. So to 3 significant figures, it's about 119 grams. So any outliers are any values which are below 82.3. So for that reason, 82 is an outlier. And also anything over 119 is also going to be an outlier. So 124 is above 119. So for that reason, 124 is an outlier as well. So we can say, therefore, 82 grams and 124 grams are both outliers. In part C, it says that one of these values is 79 grams and it's discovered to be an anomaly. So what we need to do here is to clean the data. So we need to remember what clean means. Clean means remove. To clean dirt, you remove dirt. So we're going to clean this 79 gram bird from the data. So this is going to affect these values as well. And so we need to think about what the new data would look like. So what would the new cleaned data be? Well, first of all, if a bird's removed, there were 20 birds, now one of them's removed. So that would take the total number of birds down to 19. So the new n is going to be 19. As well as this, we can work out the new total of the masses. So the new total of the masses, it used to be 2017. It's now going to be 2017 minus 79, which is the mass of a bird which we've removed. So the new total of the masses is 1938. And also, the new sum of the masses squared, that's going to be, so that's going to be what it was before, which is 205127. Now, not minus 79, but we're going to minus 79 squared. So 205127 minus 79 squared. That gives us 198886. So now we can let the calculator do the hard work. So what's the new mean? Well, the new mean is going to be 1938 divided by 19. Because that's the new total of the masses, and 19 is the new total number of birds. So what's 1938 divided by 19? Well, we can see here that we get 102 grams exactly. So that's the new mean, and the new standard deviation. So that's going to be the sum of the masses squared, where the new sum of the masses is 198886. Divided by 19 minus the mean squared, and all of that is square rooted. So again, just using the calculator for this one, so square root of 198886 over 19 minus 102 squared. That gives us to 3 sig figs 7.98 grams. So as you can see from removing the anomaly, the standard deviation is shrunk from 9.25 to 7.98. Now, on average, the deviations aren't as extreme because we've removed one extreme value. And because we removed a bird which is on the much lighter side of the norm, the average mass, the mean mass, has gone up slightly from 101 to 102. So it's affected the data as we'd expect. And so what we can do next is have a look at some box plots and how outliers are represented on them. Now let's have a look at some box plots. So, box plots are diagrams representing key features of a dataset such as quartiles, maximum values, minimum values, and also outliers. Here's just a generic example of what a box plot looks like. Okay, so box plots are used to determine other statistical characteristics and are a useful way of comparing two or more data sets. So the key thing about a box plot is these 5 vertical lines. Oops, a daisy. So 1, 2, 3, 4, 5. So these 5 vertical lines correspond to different statistics. So in order, from the one on the left moving through to the ones on the right, the first vertical line represents the lowest value, not including outliers. The second vertical line here, that's the lower quartile. This one is the median. This one at the end is the upper quartile. So because this one's the lower quartile and this one's the upper quartile, the difference between the length of this box defines the interquartile range. Finally, the final vertical line is the highest value, again not counting outliers. So a value outside of here would be an outlier, and a value to the left of this value would be an extremely low value, which would be an outlier. So, like I've said, box plots are constructed by omitting outliers. So that's just saying that the lowest value and the highest value in the box plot are the lowest and highest values apart from the outliers, respectively. Outliers are calculated according to boundary conditions, which we've mentioned before. So typically the boundary conditions are anything less than what the lower quartile is minus k multiplied by the interquartile range, where k is almost always 1.5, or anything higher than the upper quartile plus this number k multiplied by the interquartile range. Another way of defining the boundary conditions are any values less than the mean minus 2 standard deviations down from the mean, or anything greater than the mean plus 2 standard deviations from the mean. So the outliers are still part of the data. They're not cleaned and removed, unlike with anomalies. So if outliers aren't removed, but they're not here, then how are they included in a box plot? Well, after being calculated, if any outliers exist at all, sometimes there won't be any outliers. Outliers are added in afterwards outside the box plot with a cross. So the crosses, for example this one here, that denotes an outlier. So this example here, this is a box plot that has a data set with a lowest non-outlier value of 35 here, but with an outlier of 20. So this could be like the normal bit of what the distribution is. This is like without any freakish values, and down here someone's got a 20, which is just way out. So that 20 is legitimate, so it's included as a cross. If that 20 were a mistake in terms of analysing the data, that would be removed, would be an anomaly, and wouldn't show up here at all. Let's have a look at a worked example now of constructing a box plot. This is a very basic worked example. So we've got this spelling test marked out of 20, and the results are summarised below. So here are the quartiles, Q1, Q2, Q3, and the lowest and highest value. Given that there's no outliers, draw a box plot for the data. Okay, so these 5 points, the 3 quartiles, sorry, the 2 quartiles in the median, and the lowest and highest values, these 5 values correspond to the 5 vertical lines. So Q1 is 8, so we can draw a vertical line at 8. Q2 is 9, so draw a vertical line at 9. Q3 is 12, draw a vertical line at 12. Lowest value is 4, so draw a vertical line at 4. And finally, if the highest value is 17, do another vertical line at 17. You've guessed it. So that's just colour coding, 5 different colours for the 5 different vertical lines and how they correspond. When you're doing a box plot in your exam, obviously you don't need to use such pretty colours. I'd probably suggest not doing. So let's just get rid of the colours now and think about how we can complete this box plot. So bye-bye colours, just move to one side. What we need to do now, the middle vertical lines, we need to put horizontal lines at the top and the bottom to make these 3 vertical lines form a box. So we add in 2 horizontal lines like this, and finally we add in another 2 horizontal lines, which are often called the whiskers, either side of the box, which join the lower quartile to the lowest value and the upper quartile to the highest value. So to finish off our box plot, we do this. And that's the final box plot, how it looks. So that's all we need to do for this worked example. Let's now have a look at a slightly more complicated second worked example. For this second worked example, we've got some data for maximum daily gusts in knots in Sheffield in October 1992. So it's not a full month's worth, but it's 20 different gusts, which is just a measure of wind speeds. So there's 3 different parts to this one. So for the first part, part A, we need to work out the lower quartile, Q1, median, which is Q2, and the upper quartile, which is Q3. So again, you could do this manually. They're already in order of size, but I think the easiest thing, to be honest, is just to use the class whiz. And so by now you should be very comfortable using the calculator to do these. So if you're not, I'll just show you again how you could do this. So first of all, I'll just move it to the side actually. What we need to do is get in the right mode. So we press Menu, Option 6, 1 variable, then we enter the data. So just to move it to the other side so I can see the lower values. So the first value is 12. I'll make the screen bigger actually so you can see what I'm typing in. So type 12, then equals 20, then equals. This is quite tedious obviously, but it's just the easiest way of making sure you make no mistakes. Next one's 22, press equals. Move to the other side. We've now got a second 22. So if you see here, there's 2 22s. So 1 22, type in another 22. And I've got 24, 1, 2, 3, 4, 5 times. So I'm going to type in 24 5 times. 1, 2, 3, 4, 5. So 24 once, 24 twice, 24 for the third time, 24 for the fourth time, and 24 for the fifth and final time. We now have 26 a few times. So 1, 2, 3, 4 lots of 26. 26 one time, 26 for the second time, 26 for the third time, and 26 for the fourth time. Then there's 128. There's 3 lots of 30. 1, 2, 3 lots of 30. 1, 2, and 3. Then 31, 32, and finally 40. Press equals. Now we want to work out the quartiles of these data. Well, to be honest, we want the calculator to do that for us. So now we press AC, option number 2, and scroll down so we can see Q1, median, and Q3. So Q1, the lower quartile, is 24. So we type Q1 and put equals 24. Then Q2. So Q2 equals 26. Q2 is median. And finally Q3, the upper quartile, we've got this is 30. Just double check we've typed it in correctly. 24, 26, and 30. So yes, we've got it all there. We're now told that an outlier is defined as any value that lies either 1.5 multiplied by the interquartile range above the upper quartile, or 1.5 multiplied by the interquartile range below the lower quartile. So now for part B, we need to show that 12 and 40 are outliers. What we need to do now is work out the interquartile range. So the interquartile range is going to be 30 minus 24, which is 6. So 1.5 multiplied by the interquartile range means 1.5 multiplied by 6, which is 9. So this measure here, 1.5 multiplied by the interquartile range, is simply 9. So based on this figure here, Q3 plus 9 is 30 plus 9, which is 39. 40 is above 39, which tells us that therefore 40 is an outlier. Okay, because 30 plus 9 is Q3 plus this 1.5 times interquartile range, which is 39. So if I just highlight here that 30 is Q3, so 30 plus 9 is 39, and 40 lies above that. 40 is higher than 39, which is, as I've said, why 40 is an outlier. We now do the same to work out if there's any outliers at the lower end. So the lower quartile is Q1, which is 24. So we need to see if 1.5 multiplied by the IQR below the lower quartile, which is going to be 24 minus 9, we're going to see if anything is below 24 minus 9. So now we're going to do 24 minus 9. So just to say again, 24 is the lower quartile, and 9 is 1.5 multiplied by the interquartile range. And you should know 24 minus 9 is 15. And of course, 12 is less than 15. So therefore, for that reason, 12 is also an outlier. Part C, it now says draw a box plot for the data. So what we need to do here is use these measures for Q1, Q2 and Q3 to do 3 vertical lines. So if Q1 is 24, we can do a vertical line at 24. Q2, the median is 26, so we do another vertical line down at 26. And then Q3, which is 30, we do another vertical line down at 30. We have to do 2 other vertical lines, which corresponds to the lowest value and the highest value, respectively. But these lowest and highest values must not be outliers. And so if I just put here, underline outliers in purple, 12 and 40 are outliers. So that one's an outlier, and this one is. We plot with the vertical line the lowest value that wasn't an outlier and the highest value which wasn't an outlier. So the lowest non-outlying value is 20, so that's going to be our first vertical line, and our highest non-outlying value up here is 32. So therefore we do another line here at 32. So then what we do is do a vertical line joining Q1 to Q3 at the top and at the bottom. That makes the box. And then finally, to finish off, we do the whiskers, joining the lowest value to the lower end of the box plot and joining the upper quartile to the highest non-outlying value. So that's the box plot. However, we also need to include these outliers. Now the outliers, if you remember, are shown by crosses. So the outliers, which I've done here, outlined them in purple, I'm going to have 12. So I'm going to put a cross here at 12, because that's an outlier at 12. And there's also an outlier up at 40. So we do a cross here where 40 is. So 12 and 40 are the outliers, and the main bit of the box, the actual box plot here, is in the middle. And so that's this worked example finished off. Now let's talk about how we might want to compare box plots. So how do we compare box plots? Well, when making comparisons between two box plots, always ensure that you compare A, a measure of location, and B, a measure of spread, in the context of the question as well. So, some general guidance for doing this. So when comparing data, like I've said, always attempt to comment on a measure of location and a measure of spread. You need to comment on both. And there's two main ways to do this. So one way is to compare the medians and the interquartile ranges, or compare the means and the standard deviations. Notice here that you can't mix and match these measures. So you can't, for example, compare the medians and the standard deviations, and you can't compare the means with the interquartile ranges. So it's medians and interquartile ranges, or means and standard deviations. So one way I can explain this to you is that you need to compare like for like. So medians and interquartile ranges go hand in hand. They're a family. So the lower quartile is Q1, median's Q2, upper quartile is Q3. So they're one family of comparisons. The other family is the mean and standard deviations. The mean, x bar, is used to calculate the standard deviation. Remember, standard deviation formula is this, and so the standard deviation and the mean are inextricably linked together. Generally speaking though, to keep it simple if you can, the easiest way I'd suggest would be to compare the medians and the interquartile ranges. That's the easiest way to do it if you can. So let's have a look at a worked example of how we can do this. So we've got two different box plots here, and these box plots show the masses in grams of male and female terrapins. So this scale here on the bottom is masses in grams. So I'll just label this on just to make it perfectly clear. Always include units if you know them. So what we need to do now is to compare, which means to show similarities if you can, and contrast, which means any differences. So compare and contrast the masses of the male and female terrapins. So one thing we can do is compare the medians. So the median for the males, as you can see here, is 600. This line here is at 600. So just to show you that, that's 600, whereas the median for the females is 300. But you need to compare these measures in context. So in context of the question, we could say the masses of the male terrapins tended to be greater than for the females. And I'm putting in brackets why that is. That's because a male median is 600 grams, whereas a female median is only half of that, which is 300 grams. So work out and show you've worked out the medians, and then interpret that in the context of what the question actually is. Don't just put 600 is greater than 300. Say what 600 and 300 mean, and make reference to the context of the question. So that's the measure of the central tendency. We now need to do a comparison of a measure of spread. Because you've used the medians, the next thing we need to compare on is the interquartile ranges. So secondly, we can say, by comparing the interquartile ranges, that the masses of female terrapins are more spread out than the males. So the interquartile range for the females is 600 grams. From 200 to 800 is a gap of 600. Remember, interquartile range is how long the box in the middle is. So show that you've calculated the interquartile range for the females, which is 600, and the interquartile range for the males is 700 minus 400, which is 300. Remember, in the context, interquartile range is a measure of a spread of data. And so don't just say interquartile range of females is 600, which is bigger than the males, which is 300. Say what that means. Interquartile range is a measure of spread, so something like this will do. The masses of female terrapins are more spread out than the males. Then in brackets, this is the proof as to why your statement here is valid. So we've got a measure, a comparison of central tendency, the median, and a comparison of a measure of spread, in this case, interquartile range. And that does us, and that would pick up full marks. Now it's over to you to try some of these on your own. So in the books, page 45, exercise 3b, statistics and mechanics, if you were to try questions 1, 2, 3 and 4, and then check that you can do those okay by checking answers at the back, that's great. If you get stuck, obviously ask me either in class or send me an email, or even leave a comment in the video section on YouTube. So thanks so much for listening. I hope you find these questions okay. If not, you know how to get hold of me. Thanks again, and I'll see you all soon. Bye for now.